Rock here with Simpson Math. Let's discuss the difference of squares rule. To understand the difference of squares rule, you have to have a little experience multiplying binomials that are conjugates of one another. So let's do one of those. Let's take a binomial like x plus 5 and multiply it by its conjugate. The conjugate of a binomial is the same binomial, only change the sign in the middle. So these are conjugates of one another. That word conjugate is spelled like this. Okay? Now, if I multiply this together, something kind of cool happens. If I go the first time to first, I get x squared. The outer time the outer, I get the negative 5x. Inner time the inner, I get the positive 5x. And then the last time the last, positive 5 times negative 5 is negative 25. But notice a negative 5x and 5x, they're opposite signs, but they're the same quantity, so they add to 0. So this adds to 0, and we have x squared minus 25. So notice we have the square of the first term and the square of the second term with a minus in between. That happens every time, so this is called the difference of squares rule. So if I have a binomial, any binomial, and I'll multiply it by its conjugate, it will equal the first term squared minus the second term squared. This is called the difference of squares rule. Let's see if we can see all that on the screen. There we go. So sorry about that glare there. See if I can zoom in a little. Nope, I can't. I can zoom this in. Okay, duh. All right. There we go. That's a little better. So you want to have this rule in your notes. Difference of squares rule. That if you multiply a pair of binomials together that are conjugates, you always get the difference of squares of the two terms. And then that means we can factor any quadratic expression where the b is 0, or any binomial where you have a difference of squares, and secretly they don't have to be perfect squares. I'll do one where they're not perfect squares as the last example, but let's do a kind of traditional example first. So if I have w squared minus 36, okay, so it's a quadratic. The a is 1, the c is 36, negative 36, but the b is 0. So when you have a quadratic where the b is 0, in other words, you just have a binomial quadratic, it's going to factor by the difference of squares rule. So we know that one of the factors is w plus 6, the square root of w and the square root of 36, and the other one is its conjugate. That's simple. If I multiply this out, I get that. It's that easy. Okay, let's do another one. Okay, let's turn it around, because sometimes students get confused if it's turned around. What if I have 64 minus x squared? Well, the 64 is first, so you just put the 8 first, which is the square root of 64. You put the x second. You make one plus, you make one minus. We could factor out a negative and change the order, but there's no need to do that. There it's factored, okay? So that's easy enough. What if it's not quadratic? What if it's y to the 6th minus 100? Okay, well, we can at least do the first step here using the difference of squares rule, because we know that y to the 3 is 3 y's multiplied together, and y to the 3 is 3 more y's multiplied together. So if I multiply that together, how many y's are there? There's 6 y's. So the square root of y to the 6th is y to the 3. So I can go y to the 3 minus the square root of that, which is 10. And then y to the 3 plus the square root of that, which is 10. And now I have something called a difference of cubes and a sum of cubes. And there are actually rules for factoring differences and sums of cubes. But we're not going to learn that later, so we'll stop this problem here. But this could factor further. But I just want to hammer home that first step where we factor it as a difference of squares. Now, I said we'd do one where it's non-traditional, where they're not perfect squares. So if I have something like x squared minus 7. The difference of square rule still applies because it's a binomial and it's a difference. And this one's a perfect square, so that's easy enough. Just take the square root of that, which is x and x. You make one plus and you make one minus. And now I need the square root of 7. Well, 7's not a perfect square, but it still has a square root. It's called the square root of 7. And so we factored that. And this is a non-traditional factorization because we're admitting an irrational constant here. So we say it's reducible over the irrational numbers, but irreducible over the rational numbers. So some teachers might say this doesn't factor, but it does. You just have to have an irrational constant. Math made simple, Simpson math.